Hello everyone, welcome to this NPTEL course on computational process design. In the last session we have looked at the material and energy balance. What we are going to look at today is equipment sizing, uh, costing and economic evaluation. So if you look at the equipment sizing and costing, uh, these are pivotal factors in the economic assessment of the industrial processes. These are having the direct influence on the both initial investment and ongoing operational expenses associated with the process design and implementation. Again, precise cost projection stemming from equipment sizing and costing are imperative for the informed decision making regarding the process feasibility, profitability and overall economic sustainability. Further, these projections are important because we wanted to find out the investment evaluations. Again, these are important for financial strategizing. These are also important for risk evaluations within the uh, realm of process equipment development and operation. So in the early stages of the process exploration and evaluation, leveraging the approximations and established methodologies is indispensable for expeditiously and comprehensively assessing the diverse process alternatives. So what we are trying to say here is, in the initial flow sheet design we usually have some approximations, primarily because we wanted to evaluate different options faster and comprehensively. Again, swift computations and qualitative trend identification empower engineers and stakeholders to evaluate and contrast various process avenues and facilitate the recognition of promising alternatives and dismissal of less tenable options. So clearly the faster calculations based on the simple calculations is very important, because then you can find out the promising alternatives and eliminate the less tenable options. The last one is established methodologies such as Guthrie's cost estimation method. These are this can give the frameworks for estimating the equipment expenditures, streamlining the preliminary design efforts and economic evaluations. So if you look at the different estimates, so preliminary design usually have around less than 40% error. So you can see that it is attributed to the limited level of details available during the preliminary design. But despite of this is important to have, primarily because even the order of magnitude estimate serves as a valuable tool for assessing the feasibility of the various process alternatives. So that is why, even though the preliminary design has almost around 40% error, still it is important. But as we go ahead, you can see that the process design progresses into later stages. A study estimate is utilized. So study estimates are the estimate where the error is less than 25%, and you can see that in this case we have a refined cost approximations with reduced error margin of around less than 25%. So you can see that this estimate offers greater precision, primarily because of the acquisition of more detailed information during the development process. As we further go ahead in the advanced stages of process development, then we have a preliminary estimate. So preliminary estimate is where the error is less than 12% and it reflects the higher degree of accuracy. So you can see that the error margin for this estimation uh, is less than 12%, and this indicates that it is more precise assessment of the capital cost based on the comprehensive design data. Then as we further progresses in the stages of the process development, you can see that we can reduce the error further to lower value. So definitive estimate has the error less than 6%. So in this stage you can see that the detailed design information is available with us, and therefore we can make the accurate projection of the capital cost. So in this case you can see that this estimate provides a reliable basis for the financial planning, investment decision and risk assessment, as the error is less than 6%. So as we further process and design is more or less complete, a detailed estimate is characterized, where the error you can see that is less than 3%. So at this stage where the comprehensive design information is accessible, this estimation method offers an extremely accurate representation of the capital cost. Again, it supports the informed decision making and also thorough financial analysis. So if you look at the equipment sizing, so equipment sizing is crucial for determining the physical attributes and specifications of various process units, ensuring optimal performance and cost effectiveness. So accurate equipment sizing is essential for achieving efficient operation and meeting process requirements. So if you look at the equipment sizing, there are four different types of sizing which are primarily taken into the consideration. The first one is the vessel sizing and specification. The second one is heat transfer equipment sizing, and then distillation and absorption column sizing, and finally the sizing of compressors, pumps and refrigeration. So each of these four type of sizing and specification we are going to look at little bit in more detail. So let's look at the vessel sizing and specification. So calculation of vessel size and specification is conducted by considering various parameters. So we look at the flow rates, we look at temperatures, we look at the pressure and material compatibility. So this process involves meticulous consideration of factors such as vessel capacity, height, cross sectional area and pressure relating to ensure the optimal performance and safety. Similarly, for heat transfer equipment, the sizing calculations is based on the heat duties which are required, what are the temperature difference present, and the fluid properties. So typically, engineers determine the appropriate heat transfer surface areas and dimensions to effectively meet the process heat exchange requirements while considering the factors such as fluid flow characteristics and thermal conductivity. If you look at the separation units like distillation and absorption, usually the sizing of distillation and absorption columns involve the consideration of the parameters such as tray or packing heights, also the diameters of the column and efficiencies. So engineers usually calculate the column dimensions to achieve the desired specification and absorption efficiencies, ensuring the optimal performance and resource utilization. And if you look at the last type where we are trying to look at the sizing of compressor pumps and refrigeration units, uh, these are conducted by evaluating the pressure requirements present, also what are the flow rates we are trying to ensure, and temperature differentials. Again, engineers determine the equipment capacities and specifications to effectively handle process flow and meet the refrigeration needs of the system, considering the factors such as energy efficiency and operational reliability. So each of these four sizing and specification of different equipments we are going to look at in more detail. So let us start with the vessel sizing. So vessels are an important component in many chemical processes. So vessels are like reactors, tanks, all these we are considering as vessels, and their sizing and costing are critical for economic evaluations of the candidate flow sheet. So selecting the vessel volume is important. So it is based on usually how it is calculated. So usually to calculate the vessel sizing, we assume a 5-minute liquid hold up. So if we assume a 5-minute liquid hold up time, uh, with an added equal volume for the vapor flows, so you can see that we can get the volume equals to 2 into FL into tau divided by rho L. So here FL is the liquid flow rate, tau is the residence time, rho L is the density of the liquid, and 2 we have added because we are assuming that there is a equal volume added for the vapor flows. So here in this equation we can put tau equals to 5 minutes, and based on that we can calculate the V. So this is going to give us the vessel volume. So in this case again, we also make different assumptions here, like the aspect ratio L by D is assumed to be 4 for general costing purposes. So what it reflects? It reflects that we are considering the cost of the bottom and the top caps as 4 times as that of the side. So that is what we are assuming when we are taking L by D equals to 4. So if the diameter exceeds 4 feet, let's say the diameter of the vessel is more than 1.2 meter or 4 feet, in that case we are considering this design as a horizontal vessel. And in this case, when we consider the vessel as a horizontal vessel, there the important factor is to manage the space requirement instead of the structural support cost. So when the vessel is vertical direction, in that case the structural support becomes important. But whenever we are considering a vessel as a horizontal vessel, the balancing space requirement is a important factor. The third point here is to ensure the safety. The vessel pressure in gauge is set 50% higher than the actual process pressure determined from the mass and energy balance. So this is a safety factor we have to utilize. So the pressure, the maximum pressure which the pressure vessel should withstand should be 50% higher than the actual pressure which we are calculating from the mass and energy balance. So this choice also enables the integration of appropriate pressure factors as per the Guthrie's method in vessel cost estimation. So there is a book by Guthrie which is capital cost estimation. So there how we can calculate the cost of different equipment is given, or different process vessels is given. So we can find out the cost calculation from this particular book. So for vessel sizing, again for the desired temperature range, uh, consider the required material of construction as shown in the table. So in this particular table, you can see that if the different temperature ranges are there, which particular material is the most suitable, that is given. This particular table is taken from the source, a systematic method of chemical process design by Bigler, Grossman and Westerberg. So you can see that when the temperature is around 950 Fahrenheit, the best material to work with is a carbon steel. So if the temperature is around 1150 Fahrenheit, then it is 502 stainless steel. So based on what temperature we are looking at, which material is the best, that is what is given in this particular table. So the type of steel recommended for material of construction at different temperatures compatible with Guthrie's factors is given in this table. These apply to both pressure vessels and remaining equipment items. So whenever we are doing the vessel sizing, the fundamental configuration for pressure vessels typically comprises a carbon steel vessel designed for a pressure of 15 psig. So in a normal case, we use the specification as pressure specification as 15 psig, again featuring the standard nozzles and manuals. This configuration serves as an initial reference point. So whenever we have additional information, only in that case we are going to change this specification. Otherwise we will start with a base design of uh, pressure requirement of 50 psig. So this reference point for both sizing and cost estimation and can be adjusted as per specific process requirements. So whenever some additional requirements are there, then we are going to modify this base design. So vertical construction entails a cylindrical shell with dished head positions at both the top and the bottom, whereas whenever we are looking at the horizontal construction of the cylinder, this involves the cylindrical shell and two dished heads and two saddles for support. So you can see that whenever we are having the horizontal design, these additional saddle supports are required. In the context of, again, in a horizontal construction, the assembly includes the shell, two heads and two saddles. The material and pressure factors for various types of vessels is also given in the literature. In addition to that, the important point to note down here is a material and pressure factor. So this material and pressure factor, it is nothing but an empirical coefficient established by Guthrie within the costing framework. So we calculate this material and pressure factor based on what pressure we are looking at, and this particular factor is used in calculation of the equipment cost. So this factor, which is determined based on the material of construction, design pressure and vessel diameter, multiplies the base cost during the cost evaluation. Again, the table presents the material and pressure factor values for various vessel types encompassing cylindrical vessels, spherical vessels and vessels with disc head. These material and pressure factor values span from 1 for carbon steel vessel to 7.89 for titanium vessel designed for pressures of 1000 psig or higher. So you can see that if we go from low pressure to high pressure, we are going to move from carbon steel to titanium, and in that case you can see that the material and pressure factor is increasing from 1 to 7. So you can see that if I am using carbon steel only as a cladding material, in that case the increase is uh, uh, lower compared to when I am using the entire solid material. So for instance, if I am using the carbon steel, then the material and pressure factor is 1, and you can see that as we go from carbon steel to titanium, and if it is used for a cladding material, then it is increasing from 1 to 4, whereas if it is used as a solid material, then it is increasing from 1 to 7. Also the pressure factor increases as the value of the pressure increases from 50 psig to 1000 psig. You can see that the pressure factor is increasing from 1 to 2.5, and all these are having impact on the cost calculations. Now coming back to the next type of equipment sizing. So if you are looking at the heat transfer equipments, so heat exchangers are used to transfer heat between two fluids in a chemical process and are uh, commonly used in process industry. So this is a typical shell and tube heat exchanger schematic is shown here. You can see that within this shell there will be a bundle of tubes, and both the cold fluid and the hot fluids are moving in a counter current direction in this case. So typical expression used for calculation here is the heat transfer Q is given as UA delta T LMTD, where U is nothing but the overall heat transfer coefficient, A is the heat transfer area, and delta T LMTD is nothing but the log mean temperature difference. So in this case, you can see that this overall heat transfer coefficient is a empirical parameter that depends on the type of fluid, the flow rates, the geometry of the exchanger, and other factors. So we can calculate in addition to this, we can calculate this U by using the empirical correlation. So we can have the inside heat transfer coefficient, outside heat transfer coefficient, and based on the geometry then we can calculate the overall heat transfer coefficient by using the correlations, and that we can use in this equation. Similarly, the log mean temperature difference is given by this equation. So you can see that if I look at the same heat exchanger, the temperature difference I have to calculate at both the end. So the temperature difference here will be delta T1, and here the temperature difference will be delta T2. So delta T1 in this case will be what? T1 minus T2, whereas delta T2 is nothing but what? T2 minus T1. So based on this delta T1 and delta T2, then we can calculate log mean temperature difference as delta T1 minus delta T2 divided by log of delta T1 by delta T2. You can see that the log mean temperature difference is primarily used because this temperature difference is varying as we are moving from one end to the another end of the heat exchanger. So to accommodate this variation in change in temperature, log mean temperature difference is used. So another complications which come across while designing the while doing the cost calculations for the heat transfer equipment is whenever there is a phase change is taking place. So phase change is commonly seen whenever there is a condensation of one fluid is having, or evaporation of one fluid is happening. So in that case what we do is uh, we calculate U value slightly in a different way. In this case, the exchanger can be split into serial units, and the U values for each unit can be calculated separately. So for instance, here you can see that this fluid, you can see that the hot fluid is exchanging the heat, and then it is condensing. So from this point onwards you can see that the temperature is almost remains the same, which is Tc. So one fluid is uh, exchanging the heat in a sensible heat initially, and then there is a latent heat. Okay, so you can see that, whereas the other fluid, if you look at the other fluid, the temperature is continuously increasing here as we are moving from uh, point 1 to point 2. So you can see that we can have two sequential parts here. So just for the sensible heat transfer, this initial part we can take as a part 1, whereas the second part where the condensation is taking place primarily, so there we can take as part 2, and we can calculate the heat transfer area for both these parts, and that we can sum up. So you can see that when we are taking only the sensible heat into the consideration, we are calculating A vapor, which is given as Q vapor divided by U vapor into delta T LMTD. So this U vapor will be again calculated in a different way. So whenever there is no condensation, the heat transfer coefficients are lower. So you can see that this U vapor will be a different value calculated from the different correlations, whereas U condensation here, this in the second equation, this U condensation has to be calculated based on the condensation of one fluid. So you can see that we can calculate A vapor and A condensation, and both of these we are adding here to obtain the total heat transfer area. So in Guthrie's cost estimation, the basic configuration for heat exchanger is given by a carbon steel floating head heat exchanger with 150 psig design pressure, and this includes the complete fabrication. So you can see that we can use this information in Guthrie's cost estimation method, and we can calculate the cost associated with the heat exchanger. Now let's extend uh, our discussion to a next unit, which is a reactor. So the sizing of the reactor involves determining the space velocity. So space velocity is nothing but what? Space velocity is nothing but how much volume we are processing in the reactor per unit of time. So based on the molar flow rate of the liquid or gas, and it is let's say if the molar flow rate of the liquid or gas are denoted by mu, then we can calculate the space velocity by using this equation. So space velocity is given as 1 by space time, so that is given as 1 by tau. Here tau is the space or a residence time, and that is given as mu divided by rho v cat. So here mu is nothing but the flow rate of the liquid or gas, molar flow rate of liquid or gas, and rho is the density, molar density at standard temperature and pressure, whereas the v cat is nothing but the volume of the catalyst. So based on this equation, we can calculate what is the space velocity S. So the total volume of the reactor V is calculated considering the void fraction. So whenever we are having the packed reactor, in a packed reactor, we calculate the volume V by considering the void fraction. Let's say the void fraction of the particles which are there in the reactor, catalyst particles, those are there in the reactor, is let's say epsilon, and the value of epsilon is typically taken as 50%. So we can calculate V as V catalyst divided by 1 minus epsilon, where epsilon, if I put 0.5 here, I get V equals to 2 into V catalyst. Okay, so depending on operating conditions of the reactor, it can be costed as a pressure vessel, heat exchanger, or furnace. So this is very important. So depending on the operating conditions, what is important? REB looking at pressurizing the reactor, and the cost is dominated by the pressure. In that case, we can consider it as a pressure vessel. If the heat transfer is more important in the reactor, and that is what is causing the cost, in that case we can consider it as a heat exchanger or furnace. Okay. The appropriate material and the pressure factors from the Guthrie's method should be considered when estimating the cost of the reactor. Now let's extend our discussion to the next type of equipments like distillation columns and the absorption columns. So you can see that when we are looking at the distillation column, the sizing process for distillation columns entails the determination of height. So what should be the height of the distillation column, what should be the diameter of the distillation column, and how many number of trays are there within the stack. So these are the important decisions we have to make when we are doing the sizing of the distillation column. So if you are taking a tray stacks, uh, you can see that in a Guthrie's methodology, this feature a standard configuration comprising 24-inch trays constructed from carbon steel. So if you look at the Guthrie's methodology for distillation column, it involves this 24-inch tray constructed from the carbon steel. So these trays can be of plate, sieve or grid type and include necessary fittings and supports. So to facilitate costing of the vessel, tray stack and associated heat exchangers, it is imperative to first compute the number of theoretical trays and establish the reflux ratio. So when we are doing the sizing of the distillation column, the most important point to look at is how many number of theoretical trays are required and what is the reflux ratio that we have to calculate. And for that we can use different equations. So you can see that we can calculate the minimum number of theoretical trays by using this Fensky equation, which we have seen in the last session. Again, we can calculate the minimum value of the reflux ratio by using this Underwood equation. But you can see that this Underwood equation is typically is iterative, isn't it? So several iterations are there. So in order to avoid such simplified direct correlations are usually used by assuming the ideal system, and that can give you the calculation of the reflux ratio rapidly for the preliminary design purpose. The third important equation is, once we calculate the minimum reflux ratio and minimum number of theoretical trays required, we can again use the Gilliland correlation and we can calculate what will be the actual reflux ratio and tray numbers. Okay. So the correlations are given here. You can see that determining the tray number and reflux ratio, for that from the mass and energy balance. Remember, in the last session we have performed the mass and energy balance around the distillation column, and there we have by doing the mass and energy balance, we usually fix the relative volatilities, we fix the split fraction at the top and the bottom recoveries. So you can see that we usually know these values. We know alpha Lk by Hk. So this is nothing but the relative volatility of the low key component with respect to high key component, heavy key component, light key component and heavy key component. And Blk is nothing but zeta Lk, which is nothing but the split fraction of the light key component. Similarly, beta Hk is nothing but the split fraction of the heavy key component. So these values are already known from the material and energy balance. We can use these split fractions and relative volatility in the correlation. So this correlation we can use here. The first correlation is with respect to Ni. So we are calculating the number of trays here, and here I we can put as low key component or high key component, and based on that we can calculate the maximum and minimum values of the trays required. And similarly we can calculate the maximum and minimum value of the reflux ratio by replacing this I by Lk or Hk, and we can use this minimum and maximum value of N and R again in the correlation which is given here. So you can see that the actual number of theoretical trays which is required, we can calculate as gamma n into max I Ni plus 1 minus gamma n min Ni. So minimum and maximum values which we have calculated for the number of trays from this equation, we can put in this equation, and we can use this gamma n as value equals to 0.8, and we can calculate the theoretical values of number of trays or plates required. Similarly, we can also calculate the actual value of the reflux ratio using the similar equation here. So with this, then we can calculate the cost of the distillation columns. So typically you can see that these are the two schematics are shown here. You can see that when we are having a feed which is at the bubble point condition, so you can see that the entire feed will have mostly the liquid, and therefore the liquid will be coming down. So it will be trickling down from the feed tray to the bottom, whereas when we are having the feed at the dew point, it essentially involves the vapor, so it is going up. So based on this we need to have a different calculation. So you can see that the important calculation in the distillation column is to calculate the diameter. So calculation of the height of the distillation column involves the comprehensive consideration of various components including trays, reflux ratio and operational parameters. So as we calculate the number of trays, reflux ratio, and operational parameters, we can calculate what will be the height of the distillation column. Once the reflux ratio and feed compositions are determined, the flow rates within the distillation column can be computed, and then by using these flow rates and established relationship for flooding velocity, the column diameter can be calculated. So remember, in this case we usually want to operate our distillation column with 80% of the flooding velocity. So in order to maintain this 80% flooding velocity, what should be the diameter? That diameter should be the appropriate diameter for the distillation column. This is how we calculate the diameter of the distillation column. So the first step is to calculate number of trays, reflux ratio, isn't it? Then we calculate the feed compositions and flow rates, and based on that, then we wanted to maintain around 80% of the flooding velocity, and based on that we calculate the diameter of the distillation column. So these are the correlations which are used. So to calculate the column diameter, here we define UNF as a linear flooding velocity. So this UNF we can calculate as, remember, for the calculation of the diameter we require the flooding velocity. So this can be given as CSBF in the bracket rho L minus rho G divided by rho G raised to the power 0.5 into 20 by sigma raised to the power 0.2. So here you can see that rho G and rho L are the gas and liquid mass densities, and sigma is the liquid surface tension in dynes per cm. So if we are using the hydrocarbons, if you are trying to separate the hydrocarbons, typically the surface tension taken for the hydrocarbons is 20 dynes per cm. If I put that sigma equals to 20 here, this particular equation is eliminated, this particular part of the equation is eliminated, and also you can see that rho L minus rho G is typically equals to rho L. So if we put that, this original equation can be simplified immensely, and we can obtain mu NF is given as CSBF into rho L by rho G raised to the power 0.5, and this particular equation we can use to calculate the linear flooding velocity. So okay, now let us look at how we can determine the tray stack height. So the number of actual trays is given by okay, so in this case we can use the efficiency into the considerations. So typically the efficiency of the separation, if we take around 80%, so NT, that is the number of theoretical trays required, divided by efficiency, that gives us the number of trays required. And once we know the number of trays required, assuming a 2 feet tray spacing, we can actually calculate the height of the distillation column. So we choose the maximum height around 200 feet. So if we do the calculation, and if the height of the distillation column is coming less than 200 feet or 60 meter, then it is okay. If it is going beyond that, then in that case we can split it into uh, uh, different columns. So a larger calculated height will be required, that the column be split into two with liquid and vapor flows running between them. So the height of the distillation column should be less than 60 meter for all design purposes. That is what we ensure. Now let's extend our discussion on another separation unit, which is a absorber. So in a absorber, you can see that the similar methodology which we have used for distillation column we are going to use in absorber also, but there is a slight difference. In the absorber, you can see that the efficiency of the absorber is much lower compared to the distillation column. So absorber column sizes are determined using methods similar to distillation columns, taking into the accounts factors such as flow rates, compositions, and operating conditions. The number of trays in an absorber column is typically derived from the Kremser equation. So remember, in the last session we have looked at the Kremser equation. Based on that, we can calculate the number of trays, which considers the factors such as relative volatility and component recoveries. A low efficiency assumption is often used as equilibrium on trays is generally considered to be poor. Okay, so remember, we said that whenever we are trying to find out the cost related to absorbers, the efficiency value is important here, because typically the efficiency of the absorber columns are much lower compared to the distillation. The height and diameter of the absorber vessel and tray stack are costed in a manner comparable to that of the distillation columns, ensuring that the equipment meet the required specification for efficient operation and specification. So a standard assumption of 24-inch tray spacing. So this is the same as the distillation column we are using here. So 24-inch tray spacing is required. So we can calculate the minimum number of trays. We can keep this spacing between each tray as 24-inch, and based on that we can find out what is the height of the absorber column. So again, accordingly, the costing of the absorber column we can perform. So this provides the practical guideline for tray layout and performance optimization. So in addition to tray based absorber designs, if let's say the absorber column is a packed bed, in that case, again we can use the same Gutierrez cost methods. So in this case, we can use the valuable data and insights on the costing and selection of the various packings for absorbers, and this can aid in our decision making. So what are the packings we are using inside the absorber column? Based on that, different cost factors we have to include, and based on that we can calculate what will be the cost associated with the absorber columns, and these design values then we can use for optimization. Now extending the discussion to the other equipments like pumps. So when we are having the pumps, the theoretical work for pumping liquid is typically calculated as V delta P. So how much is the pressure drop causing across the pump into what is the volume we are handling. Based on that we can calculate the theoretical work required by the pump. So the brake horsepower for the pump can be determined using the formula. Remember, all these pumps are usually specified in terms of horsepower. If you go to the market and buy a pump, it is given in terms of horsepower. So what is horsepower here? We can calculate the rating of the pump in terms of the horsepower as mu into delta P divided by rho np eta P and eta M. So here you can see that mu is nothing but what? Mu is nothing but the molar flow rate, whereas P1 and P2, these are the upstream and downstream pressure. So P1 minus P2 is nothing but the pressure drop across the pump. Rho is the density, eta P is the efficiency of the pump, whereas eta M is nothing but the efficiency of the motor. So based on that we can calculate the horsepower of the pump. So again for the pumps we can use the Gutierrez cost estimation method to calculate the capital cost. So if we are having, let's say, a centrifugal pump, typically in a Gutierrez calculation you can see that these are made up of cost. If you look at the pumps, these are made up of cast iron and operate below a 250 Fahrenheit with a suction pressure of around 150 psig. Cost correlations of the reciprocating pumps are also available in Gutierrez cost estimation method, and these are offering insights into the costing and selection of the pumps based on the specific operating conditions and requirements. So you can see that which pump we should be using, that depends on what pressure we are looking for. So if you are looking at the higher volume, then in that case centrifugal pump is used. But when we are looking at the higher value of the pressure change and low volume, in that case we are using the reciprocating pump. Again, the pump efficiency and motor efficiency play crucial roles in determining the overall energy consumption and performance of the pumping system. So highlighting the importance of selecting the efficient pump configuration for cost effective operation. Okay, so now let us extend our discussion to some other equipments like compressors and turbine. So ideal assumptions are made for gas compression in sizing the compressions and turbines. So we assume that the gas is ideal. Again, we can divide these equipment into centrifugal compressors or reciprocating compressors. So with relatively high capacities and low compression ratios required, in that case we use the centrifugal compressors. When we are looking at the low capacities and high compression ratios, then we are using the reciprocating compressors. So again, if you are looking at the adiabatic compressor, the ideal compression work can be calculated from the change in enthalpy. So the work can be given as mu into delta H. Here mu is nothing but the molar flow rate, whereas HV is nothing but the enthalpy of the vapor, gas enthalpy, and you can see that delta H is the change in the enthalpy. So assuming the ideal system, equation can be, again, this is nothing but delta H. So delta H can be given as Cp dt. So we can write this W as mu Cp dt. So here you can see that mu Cp into delta T we are having. Then this Cp value for the ideal gas, this Cp value can be represented in terms of the heat capacity ratio, Cp by Cv. So this is given as mu into gamma divided by gamma minus 1. Here you can see that this gamma is nothing but what, Cp divided by Cv, and it is taken as 1.4 for the ideal system, and the R here taken as a universal gas constant. So assuming the ideal isentropic adiabatic expansion, we can calculate what will be the temperature T2 from the pressure ratio using this particular equation. So T2 divided by T1 is given as P1 by P2 raised to the power gamma minus 1 divided by gamma. Here gamma value is nothing but 1.4 for the remember in the last slide we said that gamma is given as Cp by Cv, which is equals to 1.4. So substituting this particular temperature in a earlier equation, so we get the expression for the work W is given as mu into gamma divided by gamma minus 1 into RT1 in the bracket P1 by P2 raised to the power gamma minus 1 divided by gamma minus 1. So this is the equation we have to use when we are looking at the work required, theoretical power required for the compressor. So when assessing the efficiencies of the compressors or turbine, a standard practice is to select the efficiency value eta equals to 0.8 for compression and for expansion work efficiency. For a compressor driven by a shaft driven electric motor, if you are having a compressor driven by a shaft driven electric motor, then the efficiency value is equals to 0.9. But when we are using the standard practice where the eta value is 0.8, again if the turbine is used as a driver, in that case the efficiency value is 0.8. Consequently, the actual horsepower for the compressor is calculated by using this equation. So we can calculate the actual horsepower as, once we get this the theoretical power required, W divided by eta m and eta c, where eta m is nothing but the motor efficiency and eta c is nothing but the compressor efficiency. If you take that into the account, we can calculate how much horsepower is required. So we need to calculate how much horsepower is required for particular compressor, because then we can buy the compressor with that specification from the market. So you can see that if the motor driven compressor is there, in that case it is 1.39 into W, whereas when it is turbine driven, then it is 1.562 into W. Very often you can see that the compressors are based on the waste heat turbine or something else, isn't it? So whenever the turbine is used for running the compressor, in that case the equation we have to use is 1.562 W. Whenever the compressor is running based on the electrically driven motor, in that case it is 1.39 into W. So furthermore, it is essential to limit compressor sizes to maximum horsepower of 10,000. So we don't want it to have the compressors more than 10,000 horsepower. Okay. If you look at the Guthrie's method, which is there in the book, Guthrie's cost estimation book, if you look at it includes different configuration for the compressor cost calculations. The primary configuration typically involves a centrifugal compressor equipped with carbon steel circuit operating at a maximum pressure of 1000 psig. So this configuration encompasses the motor driver, coupling, base plate and associated components. So this particular calculation is already there in the book, you can find out. So now remember that when we are using the compressors, we assume that it is adiabatic compressors. So typically because of the compression, the temperature increases, and we don't want to have the temperature of the equipment going beyond a particular limit. So in such cases, in order to eliminate this particular problem, typically the compressors are used in a staged manner. We don't use a one big compressor. Instead of that, we use several compressors, smaller compressors, in a staged manner. Okay, so stage compressors are utilized to achieve a desired increase in gas pressure with reduced work requirement by incorporating the intercooling between the compression stages. So we can intercool the units. Again, isothermal compression, while physically, if we are looking at the isothermal compression, it is physically unrealistic, because whenever you are compressing a particular gas, it is going to increase the temperature, isn't it? So you can see that that is also one reason why a staged compressions are required. So you can see that the stage compressions showcase the efficiency improvement achieved through the intercooling. So if you are having the intercooling, then we can have a higher efficiency. For a fixed number of compressors, maximizing work requirement in staged compression occurs when compression ratio are equalized across the stages. So what it means is, the efficiency increases if you are using all these compressors with same compression ratio. Okay, so you can see that if I am having a first compressor, if it will have a compression ratio of P1 by P naught, second will have P2 by P1, third will have P3 by P2, and if all these compression ratios are same in a staged wide compression, then my efficiency is maximum. So work done in such staged wise compressors, stage compressors given as W is given as mu into N, where N here is the total number of compressors used, into gamma divided by gamma minus 1 into RT naught, uh, and in the bracket it is Pn by P naught raised to the power gamma minus 1 uh, divided by gamma n minus 1. So you can see that this particular equation is used when I am having n such compressors in series one after another. A typical schematic is shown here. You can see that there are n compressors one after another, and you can see that the output of one is given to the another, and in between you can see that we can have interstage cooling we can have. So based on that, we can have a higher efficiencies. Okay, so in the same equation, in this particular equation, if we take n tends to infinity, the isothermal work required is given as W is given as mu RT naught ln Pn by P naught. Now let's look at the reciprocating compressors. Remember I said that the centrifugal compressors are used when you require the higher volume, isn't it? So but when you are looking at the large change in the pressure values, in that case the best compressors to be used are reciprocating compressors. So reciprocating compressors operate by effecting a pressure change through a mechanical volume changes using a piston and cylinder setup. So you can see that in this case whatever the volume is there, that is getting compressed by using a piston here. Okay, these compressors are best suited for applications requiring low capacities and significant pressure changes. The theoretical power for reciprocating compressors can be calculated based on specific equations considering the factors like clearance and compression efficiency, and the equation which is used for calculating uh, the the work required is given by the same equation as we have seen earlier, except that this entire equation is divided by one more factor, which is nothing but 1 minus C into P2 by P1 raised to the power 1 by gamma minus 1. So this is the additional factor is divided with respect to the previous equation. So remember, this is the previous equation. So this equation is divided by additional factor which is given by this in the reciprocating compressors. So again, in this case, the selection between the centrifugal and reciprocating compressors depends on factors such as gas flow rate and desired pressure increase, with guidelines available in references like Perry's handbook. So you can see that if you look at the reciprocating compressors, there are these 4 stages are required. So in the first stage, what we are doing is in the uh, compression cycle, in the first stage between 1 to 2 we open and take the gas inside. From 2 to 3 we compress the gas, then from 3 to 4 we exhaust the gas, and again from 4 to 1 there is the expansion taking place. So all these 4 stages are involved when we are looking at the reciprocating compressors. Now, again looking at the another interesting aspects in the cost calculation which is important in the process application. So very often we require some of the chemicals to be put at a lower temperature. So typically if you look at the production of ammonia, in production of ammonia the nitrogen gas is usually kept at a lower temperature, isn't it? Hydrogen is kept at a lower temperature, isn't it? So in such cases we require the refrigeration. So refrigeration is essential when a process stream needs to operate below approximately 300 Kelvin. So requires consideration of a refrigeration cycle. So refrigeration system may need to be designed to cool a uh, stream with a focus on balancing capital and operating cost by selecting the appropriate number of refrigeration cycle. The pressure enthalpy diagram is a valuable tool in understanding the heat absorbed from the process stream and the heat per unit mass of the refrigerant in the refrigeration cycle, and Q is the heat absorbed from the process stream at a sub-ambient temperature. Q dash is the heat per unit mass of refrigerant. Here a single cycle requires the maximum work and cooling water QC, while a large number of cycles require minimum work and QC. So you can see that when we are looking at the refrigeration cycle, it involves these four stages. Okay, so the first stage is we compress the gas, isn't it? Then from first stage of the compressor, then there is a cooling of the gas taking place in the second stage. Then the throttling is taking place. So valve is there, so where the throttling process is happening, and in the fourth stage then evaporation is taking place. So with these four stages the refrigeration is performed. So if you wanted to look at the pressure and enthalpy diagram, this is what is happening. In the first stage when we are compressing, you can see that the pressure is increasing. Okay, so enthalpy as well as pressure both are increasing when we are compressing. Then in the second stage what we are doing is we are cooling, so the temperature is decreased, so that is why delta H is decreasing here. In the third stage you can see that the throttling is taking place. So in this case you can see that the volume is increasing, so pressure is decreasing and volume is increasing. So we are moving from 3 to 4 here, and in the fourth stage there is a evaporation is happening. So you can see that with this cycle you can see that we can perform the refrigeration. We can reduce the temperature of the process stream. So a coefficient of performance is the important factor when we look at the cost estimation of the refrigeration. So whenever we wanted to look at the performance of the refrigeration, the important factor which is one has to look at is the coefficient of the performance. So coefficient of performance is defined to relate the work and the heat rejected in the refrigeration system, with a typical guidelines suggesting a coefficient of performance around 4 for design purpose. So Cp here is given as Q dash by W dash. Again, typical cycle, W is given as Q by 4 and QC is given as W plus Q minus 5 by 4 Q. And the compressor driven by electric motor, we can calculate WB. So this is nothing but the work required, so which is given as W by eta M. So eta M is uh, the motor efficiency, and eta C is nothing but the compressor efficiency. Okay, so we can use these values to calculate WB. So another important point to look at is there are several constants which we need to satisfy when we are performing the refrigeration. So the refrigerant must remain below the critical point in the condenser. So T condenser maximum, you can see that should be equals to 0.9 TCR. Again, if cooling water is used, then T condenser maximum should be greater than temperature of the cooling water plus delta T minimum. So in the evaporator, refrigerant and the pressure should be chosen so that temperature of the evaporator should be greater than the temperature of the boiling of the refrigerant. Also the evaporator pressure should be chosen greater than 1 atmosphere, so that there is a we are avoiding the leak to the evaporator. Okay, Finally, we choose the temperature drop around 5K. So you can see that when we are going for heating, the temperature difference usually used in the heat transfer calculation is 10 degrees. Whereas when we are looking at the refrigeration, the temperature difference, minimum temperature difference required is around 5 degree or 5 Kelvin. Okay. So for both the evaporator and condenser, we require the delta T of 5 Kelvin. Cost estimation. If you look at, so see, we have seen how we can calculate the size of different equipments so far. Now we will be looking at how we can calculate the cost for different equipment. So you can see that equipment cost increases non-linearly with equipment size or capacity and can be expressed using power law expression. So we can calculate the actual cost. C is given as C naught into S divided by S naught raised to the power alpha. Here the exponent can be less than 1. So you can see that S naught and C naught are the base capacities and cost. So if you know the base capacities and cost for the new value of capacity, we can calculate what will be the cost. So for a different equipment, this value of alpha is defined, and we can find out these exponent values from the literatures. So this non-linearity reflects an economy of the scale where incremental cost increase with larger capacity. So if we are increasing, if the larger capacities are there, in that case the cost increases uh, uh, with a lower rate. So based on that, the non-linear equations are used here. So again, for a pressure vessels, service capacity is related to volume while the cost is linked to the weight. So weight of the metal required. So remember, when we are making the pressure vessels, how much material is required for making the particular vessel is important, and that is kind of reflected in the cost. That, so which is proportional to the surface area. So okay, you can see that for a spherical vessel we can calculate volume as pi by 6 d cube, and then we can calculate the weight of the spherical vessel. So that will be given as density of the material into thickness of the vessel into area. So remember, area is important. So weight is proportional to the area, and if you see that whenever you do the calculations and you wanted to minimize the amount of material required for manufacturing these vessels, you basically minimize the surface area. So in this case, again, the weight is represented in terms of the area. If I put the diameter in this particular equation, you can see that the cost is proportional to the weight, and it is proportional to the volume raised to the power 2 by 3. So it is proportional to the area, but when we are having volume, it is proportional to the volume raised to the power 2 by 3. It is not directly proportional. Okay, so it is non-linearly related with the volume, but it is directly related with the area. If we are having the cylindrical pressure vessels, in a cylindrical pressure vessels, both length as well as diameter is important, and therefore the cost is calculated as C naught into L by L naught raised to the power alpha into D by D naught raised to the power beta. Here alpha and beta are the exponents which we can find out from the literature. So here L naught and D naught are the base size and base length and base size for which the cost are available, but for any other length and the diameter, we can calculate the cost by using this particular equation. So again, additionally, if you look at the Guthrie's uses the log charts to represent the cost. If you look at the Guthrie's cost estimation book, you can see that there is a log C versus this cost is represented. So you can see that the cost we have represented as what? CB, which is a base cost, into S by SB raised to the power n, isn't it? So here SB is the base value of the uh, particular variable, isn't it? So it could be diameter, it could be length, isn't it? So if we take a log of that, what we get is log C is given as log CB by SB raised to the power n. So this first term is nothing but the intercept, whereas n into log S is there. So n is the slope of the curve, whereas the log S is the nothing but the variable, isn't it? So you can see that the log charts which are given in the Guthrie is cost estimation book actually follows the second equation. So log C is plotted with respect to log S. Okay, so the slope of the chart corresponds to the exponent n, while the cost deviation in Guthrie's data can be, if you look at how much it is deviating with respect to the actual values, around 20% is the deviation. Median data is typically used for preliminary design purposes, again to adjust this cost for inflation and updated factor. So remember that the inflation is also going to increase the cost, and for that update factor is used, and this update factor can be obtained as present cost index divided by base cost index, and this update factor is used when we are calculating the actual cost. So uh, in Guthrie's modular method, it provides a structured approach to estimating the equipment cost by considering various factors and cost module. The method involves breaking down the total cost of equipment into different components. So these are there are different components are there, like base cost is there, then the modular factor is there, then material and pressure factor is there, and installation cost is there. So bare module cost is calculated as the product of the base cost and the module factor. So it is given as the bare module cost, BMC, is given as the base cost into module factor. Again, the uninstalled cost is determined by multiplying the base cost with material and pressure factor. So uninstalled cost is base cost into material and pressure factor, and the installation cost are calculated as a difference between the product of the base cost and the module factor and the base cost. So this installation cost can be represented as base cost into the module factor minus base cost. So that is given as base cost into module factor minus 1. The total installed cost is the sum of the uninstalled cost and the installation cost, and it is defined as total installed cost is nothing but base cost into uh, 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 MFP plus MF minus 1. So you remember, in this case MF is what? MF is nothing but this. MF is a module factor, whereas MFP is nothing but the material and the pressure factor. So we can use this and we can calculate total installed cost as base cost into MPF, which is nothing but pressure factor, and the MF is the module factor minus 1. So updated bare module cost is calculated using an update factor. Remember I said that because of inflation we have to account the update factor to adjust cost from the base year to the present year. So we might be having the base cost with respect to a particular year, and we are interested in calculating the cost at the current year. So in that case we have to calculate the update factor, and that update factor we have to multiply. So module factor is influenced by the base cost, and specific values are assigned based on the different ranges of the base cost. The material and pressure correction factor are used to adjust costs based on the type of material and pressure involved in the equipment design. That is what we have seen. Depending on what material we are using, what pressure conditions we are using, based on that the cost will increase or decrease. Okay. And the final point here is the Guthrie's modular method simplifies the cost estimation by incorporating factors like materials, pressures, construction types, inflation adjustment to provide the comprehensive estimate of the equipment cost for industrial processes. So you can see that almost up to 20% error margin we can calculate the cost for different equipment and installations, and that we can use for making the decisions. So this is all for the equipment sizing and cost estimations, and we stop here. Thank you everyone.